Back, here's day 12 of Advent of Code 2023 solution in MATLAB. So again, I've just taken the demo input and I have, just popped in a little text file. So then I used like recursion and dynamic programming to solve this today. This is by far the hardest solution I've worked on this year. It probably took me an embarrassing amount of time, like many hours, probably more than 5 hours I spent on it. First thing I do is just read those lines in, as we said, oh, it's not the demo code. Reading the demo code, and then I pre-allocate a results array for the number of combinations for each line. So for each line, I just simply extract the springs map. I also so let's just look, I'll show you what data looks like. And then I also just extract the counts. So the way I decided to solve it was I would call a function, and the function you just pass in the springs and the counts, and it would return a number of combinations. But the way it actually works is so for this spring, this counts. What it actually does is it considers where it could place this first spring. So the way it does it, the first thing it does is it trims off the end. Oh, sorry, I also appended a dot to the end, so there was always a close of every set of line springs. There was always a closing statement at the end. Just made it easier for like not overflowing my array if I want to do +1s to check the end. So what it actually does is it checks where it can place this first one. So to optimize it a little bit, obviously we need to put at least 4 more characters into the end. So we need to put at least 4 more springs in, and the spring is also going to need 2 gaps before the springs. So to fit 3 in, you need 4 spaces, and to fit 1 in, you need another 2 spaces. That's 6. The last 6 spaces of this array can't have this spring starting in it. So I trim off the end. So I take the last 6 digits off. So there's enough space to fit the remaining springs. Then it leaves me only one potential starting point for this one. So that starting point has to start there. So the confusing bit for this is calculating all these possible starting points, because there's actually 4 conditions that you need to be able to start it. Where is it? This one. So the only place you can start. So to start this spring, you can't start it, say, here, because if it started there, these hashes before it would no longer be hashes, because this one starts here. So what you need to do is there's 4 things you need to check. You need to make sure that there's no hashes. So say this was a hash, the only place one could start would be there. It can't start here, because in this hash there would be no spring allocated to it. So you have to check that there's no hashes before the starting point. You have to check that it's potential for the number of the length of the count to all be springs. So if this was a 4, obviously it couldn't start here, because this 4th one is a break. So we need to check that for each starting position, that there's no hashes before it, that it and the number of counts can all be springs. That you can have a break before it. So say you wanted to start it. So you can't start it here, because there can't be a break before it. We know that's a spring. So number 1 can't start here, because there can't be a break before it. Again, there needs to be able to be a break after it. So again, your spring can't be here. It can break after, but it can't break before. So that's definitely, none of these is definitely the location for spring 1. And then the final, so there you 3 checks. There's no hash before the starting point. They all are possible to be hashes. There can be a dot after it, and there can be a dot before it. So for 3, obviously, if it was 3, when we get to 3, it's this one. So there can be a dot before it, there can be a dot after it, and they all can be strings. So actually, this one could be the 3 as well. But sorry, to explain what it actually does. It comes in the top, and we give it the springs and the counts. And every time, all it does is tries to position one set of springs So when it comes in, it just considers this is the first set of springs. It just considers the first element of counts. Just considers the first element of counts and works out where it can position it. It works out where it can position it based on all these starting positions. And if there's no starting positions, then if we can't place the springs anywhere, then obviously there's no that's not a combination we can use. So we just exit out of it. If the number of springs, if the number of sorry, I'm getting a bit. I'm trying to lose my train of thought here. I am quite new to doing these, so I'm not sure whether it's best to go line by line through the function and explain how it works, or look at the overarching principles of it. I'll go for the overarching principles first. So for this example, it works. So this example, the first time it comes through, it just tries position number 1, and it works out the only position it can be is here. So what it does then is it for all the starting positions, it loops through them all. In this instance, there's only one, and it recursively calls the function again. So it calls process lines again. But what it does is it trims off the starting point and its break, and then it'll call the function again. But this time it's just going to pass this as its spring list, and it's going to remove the first count. So now springs will become that, and the counts will just become the bottom 2. And again, we just keep recursing in to the point where we get a spring list that looks like this, and a single count. And if that happens, so if we just have one spring list, then the number of combinations for a single spring list is the number of potential starting positions. So if we only have one count left, then the number of combinations for that small part of the problem is the number of potential starting positions. And then that returns out, and that adds onto this one, which returns out and adds onto this one. So then it's a dynamic programming problem. So every time what we're doing is we're just trying to place the first spring. It places it somewhere and then removes the start of the spring list and removes the first count and calls the function again. Just keeps going until there's only one count left, and it works out where it can position that last count, and then it recurses all the way back up. To optimize it, I did add some indexing. So I have a persistent value of d, which is the dictionary where you have just a char to double lookup. So I create my dictionary key, which is just a spring list, and then the ASCII symbol for all the counts. Just concatenate it together. So then first thing it does when it comes in, it checks if it's checked that key before. If it has checked that key before, it just sets n to that value because we've already checked it. Just returns it. And right at the end, when it finishes, whatever n was for that spring and that count, it just sets it into the dictionary. So obviously, some of the longer ones, you process the last, say, 5 digits and try to position one spring in it. You'll do it over and over and over again because obviously there's millions of combinations for the first half of the spring. So the caching saved a lot of time. Using the dictionary seemed to be pretty effective. This is the subspring part where I just extract the springs at the start where it could potentially be, leaving space for the remaining count at the end. If there's no more remaining counts beyond this one, then we don't change it. This is just some lookups where it can be and where it can break. If there's nowhere it can be, then we've gone down an alleyway that's not possible, so we get rid of that. And this is just that 4-way lookup I was talking about before, where we check for these 4 conditionals on the starting positions. So yeah, so now if we run it, it runs lovely and fast for the demo code. If we run it for the full code, it runs pretty fast for part 1. Part 2 is much slower, but I spent so long on this that it works, and I'm done. That worked so fast because of the dictionary. The dictionary is still persistent, so it already had a head start on the solution before it even got going. So I'll run it again with the dictionary clear. So it takes about 3 or 4 seconds, I think. There you go, 4 seconds, and there's the same solution. Obviously, when the cache is built up, it runs like super fast. But if you run it with no dictionary, no cache, it takes a bit of time to run. Yeah, so that's my solution for part for day 12. So in summary, I have a function that takes these two inputs. And it looks for all the potential starting positions and then calls itself and then trims that off the start and calls it again. So for example, so in summary, what it actually does is this. So if this was your these are the arguments into this function, it would just look where it can place the first spring. So it trims off the end so there's enough space to place these. So it gets rid of all this. Then it looks where it can have a 1 and a dot. So the only place that you can have a 1 and a dot in here is here. So you have a 1 and a dot, and obviously before it is a break, so that's great. So that's the thing, because there's no hashes before it. It can be a break before, it can be a break after, and it can fit one spring there. So that's our only potential starting position. So what I do then is I just trim this off the start, take this off the start, and call the function again. So now it's going to look for where it can place 1. The only place it can place it is there. So it's going to trim those off the start. And then call it again. And now the last time it comes in, there's only 1 count. So it just looks for all the positions it could place that count, and then returns that value. So if it can place it in, one place, it just returns 1 up all the way up the chain, and then we get 1 combination for the first one. And that's kind of how it works. Sorry this video was so rambling. I've spent a lot of time on this problem, and it's a pretty hard problem to talk about. And I guess I'm using a vocabulary that I'm not used to. So I am an electrical engineer. I never really talk a lot about programming to others. So I guess these videos will help me with my language and like the terms I should use to refer to different parts of the code. Thanks for watching.